a big round of applause to Alexandros Karatzoglou, Scientific Director, Telefonica Research.
Thank you. Thank you for the introduction. This talk, as mentioned, is about deep learning on recommender systems. And recommender systems are nowadays ubiquitous, right? Here are two examples of probably the most famous ones, the Netflix recommendation system and the Amazon recommendation system, but they're obviously not the only ones. Actually, the talk afterwards is by Oscar Thelma is about the Pandora recommendation system, which is about music, right? And if you look at the types of algorithms that were used in what's going on? Okay, in recommender systems. Whoops. Well, yeah. Okay, this should have been matrix factorization, yeah. But the types of algorithms that have been used in the area of recommender systems, they mainly deal with the data in the form of a matrix, right? Old school recommender systems represent the recommendation problem in the following manner, right? You have a matrix where you have the users and the items that you want to recommend, and you fill in this matrix with the type of user interactions that you have between the user and the item, right? And then you can do all sorts of things with this matrix, right? You can compute similarities between items using, for example, cosine similarity or Lagarde similarity. Or you can actually factorize this matrix and use the factors of this matrix using, for example, SVD, singular value decomposition, to reconstruct the full matrix, right? And using the reconstruction of this full matrix, you can use that for recommendation. This is, let's say, what has been the state of the art in recommendations over the last 8 to 10 years. But obviously, since 2013 or 14, more or less, deep learning methods have entered into the area of recommender systems and have had a significant impact and have changed the way we see the recommendation problem. Now, why would we want to use deep learning methods? I'm sure all of you know that deep learning methods work quite good, right? Now, here's an illustration of just how good they work. The first plot is actually the error rate of the ImageNet challenge. This is a challenge where you have to recognize objects on an image, right? This is basically an image classification task. Right? And this is the performance of the best technique up to 2015. Nowadays, it's even better, right? What is interesting here is that when deep learning techniques were introduced in 2012, there was a big jump in performance. But what is even more interesting is that since 2015, deep learning methods are better than the human performance, which is actually represented on the red line in recognizing images, right? And we have similar developments in the area of of audio to text transcription, right? Of recognizing spoken words, right? You can see here the red line is again the error rate of a normal human transcribing words, spoken words, right? And nowadays, deep learning techniques are actually close or even a little bit better than that, right? Now, this is one of the reasons why we want to use deep learning, right? The second reason is if you look at the traditional sort of machine learning pipeline, right? You have some data, right? Let's say you have images. You extract features out of these images, or this audio, or this text, whatever it is, right? And then you take these features and you pass them through your algorithm, right? XGBoost, gradient, logistic regression, whatever it is, right? To accomplish your task, object classification, let's say, right? What deep learning methods allow you is actually to get rid of the second, to automate, if you like, the second task, right? To automate the feature extraction process, right? In deep learning techniques, the feature extraction process is actually part of the algorithm, right? Part of your model. And this, of course, makes it much, much easier to run these algorithms, right? It's much less manual work. So in some sense, you can argue that sort of deep learning brings us one step closer to, but just a little step closer to true AI, right? Because we have automated one more part of this process of doing machine learning or artificial intelligence, right? And the third reason why you want to use deep learning techniques in recommender systems is that you can actually do a lot of model engineering with deep learning techniques, right? You can use one part of your model to deal with image data, another part of your model to deal with audio data, if you have that, another part of your model to deal with the user interaction data, and then bring it all together, right? You can actually you can actually engineer your model in a way that suits your data, right? So you can build almost arbitrary complex architectures with these models. And finally, usually when you deal with these recommendation systems, and that's certainly the case in Pandora, for example, which deals with a huge amount of users, you have also huge amounts of data, right? So, and it's been shown that these deep learning models, these deep neural networks, actually the performance of this model scales very, very well with the amount of data. And this is not exactly the case in, let's say, traditional machine learning, right? So what are the main sort of research directions in deep learning and recommender systems? So we've done quite recently a review of the literature, if you like, and we have also done ourselves some research in the area. And we have sort of identified these 4 topics where deep learning is used in recommender systems. One is learning item embeddings, and this is actually related to the area of natural language processing where word embeddings have been very, very popular. The second one is using deep learning techniques for building collaborative filtering algorithms. So using these techniques directly applied on the user item interaction data. The third one is using deep learning methods to extract features out of the content of the items. For example, if you're dealing with music recommendation, you might actually want to analyze the audio in the song so that you can map certain characteristics of the audio with the preferences of the user, right? So deep learning techniques have been used there quite a lot. And finally, what we call session-based recommendations, where we actually try to use deep learning techniques to model the structure of the data, and I'm going to go into more detail about that a little bit later. The first, as I mentioned, the first sort of area where these techniques are used are item embeddings and word-to-vec models. So how many of you know about word-to-vec? OK, quite a few, but I'll give a brief introduction. So word-to-vec is actually a deep learning technique or a neural network technique, because it's actually not that deep, to embed or to learn embeddings of words that have certain properties. We're going to see what kind of properties. What the main properties, what you want to learn is you want to learn a vector representing a word so that this vector is similar to the vectors that represent synonyms of these words, right? So you want to learn this kind of space where similar words are closely related also in this latent space, right? And one of the main sort of features of this algorithm is what is called the context window. And a context window is essentially a part of a phrase, a 6-part or 7 words of this phrase, where the middle word is what is called the target word, right? And the 3 words around are the context words. Now, what do we do with that? Well, we actually built this small neural network here, which has basically 2 layers, right? An input layer and an output layer, right? And it's actually symmetric, so the size of the input is as big as the size of the output, right? And we take, here in this example, we take the first 4 or 5 words in the phrase, and we try to predict the 6th word, right? So we have a sort of classical classification problem. How do we enter these words here? We do a one-hot encoding of these words, right? So we use a one-hot encoding in the input and try to predict a one-hot encoding of the sixth word, mat, in the output, right? So obviously, if you have a lot of text, imagine Wikipedia, right? You can take this window here, this context window, and slide it over all of your text, right? Always putting the 5 words before in the input, trying to predict the sixth word, right? And you can, in this way, learn a model that should, in theory, be very good in predicting what word comes after 5 arbitrary words in a phrase, right? But that's not really the interesting part here. The interesting part is that once we've learned this model, we have actually a layer, the last layer here, the input layer, which for every word has learned a vector of the dimensionality of the hidden layer. Right? So we learn here a matrix that is as big as our vocabulary times the dimensionality of the hidden layer. We can use that to represent then each word that we have actually we have in our vocabulary, right? So this is the main idea behind Word2Vec. There are 2 versions of Word2Vec. This is called here the SIBO version, continuous bag of words. And this is the skipgram version, which actually inverts the problem, right? Given the word in the middle or the word in the end, we are trying to predict the words around this word, right? But essentially, they're more or less doing the same thing. Once we've completed this task, it turns out that these embeddings that we learn, these vectors that we learn, have nice geometric properties, right? For example, if you take the vector for the word king and subtract the vector for the word man and add the vector for the word woman, you get something that's very close to the word queen. Right? And now there are different versions of this algorithm as well. I'm not going to go into the details, but how can we use this kind of algorithm in recommendations? Well, it turns out that a lot of the natural language processing algorithms can be used in recommender systems, quite almost without modification. For example, imagine that you have a customer on Amazon that has purchased maybe 30 items, right? So what we can do is we can put, let's say, the first 4 items that he purchased and try to predict the 5th item that he will purchase, right, in the output of this classifier, right? Then we can slide this window and then take the 2nd item up to the 5th item and try to predict the 6th item that he purchased, et cetera, right? We can do this task, we can do this exercise over all the items that all the customers have purchased, right? And in this way, we can learn very, very good representations, right? Dense representations, vector representations of these items. Once we learn these representations, we can use them in all sorts of other tasks. First of all, we can use them directly to do recommendation by computing the similarity between items, right? Or we can use them in other algorithms as input, right? Once we need an algorithm to use a representation of an item, we can use this representation, right? And this, in fact, has been used exactly in this way, right? That's the first sort of way. The first publication, let's say, was in 2015, and it was called Pro2Vec, and it was using the skipgram model. And similar works have been done with bags of items. For example, that was quite useful when you're trying to predict items in a basket. Imagine you're going to the supermarket and purchasing items, right? So here the input is the basket of items, and the output is all the other baskets that the user has purchased in the past, right? And again, this model has been extended also to include a user profile. So this is a very, very popular let's say, class of methods that are currently used in recommender systems, and there are many, many extensions to this, right? But obviously, for the lack of time, I'm not going to go into all of them, right? Another class of methods that is used quite a lot is what is called, as I mentioned, deep collaborative filtering, right? And let's say the workhorse of deep collaborative filtering algorithms are autoencoders. Okay, and maybe let's go directly to the example. So how do autoencoders work? Again, autoencoders are basically deep neural networks where essentially what you're trying to do is predict at the output the input, right? Passing through some kind of narrow hidden layer, right? So you take the input, you project it down into some kind of lower dimensional space, and then the decoder takes this lower dimensional representation and tries to decode this lower dimensional representation to the original data set, right? So here the task is exactly reconstruct the input at the output, right? You want to have exactly what is in the input also at the output, right? But what can you do? You can actually try to slightly corrupt your input, and with corrupted input, predict the output. For example, let's say you're watching Netflix, and you have watched 20 movies, right? How can I use the autoencoder to recommend new movies to you? Well, I can just take these 20 movies that you watched and remove one movie, right? And use that as an input. And at the output, try to reconstruct all the 20 movies that you watched, right? In this way, the autoencoder learns what the relationships between the different items that you have watched, right? And because many, many people have many, many similar tastes, many of these patterns will be repeated, right? So if you watch Star Trek, there's a good chance that you have watched Star Wars as well, right? So the autoencoder learns this kind of patterns, right? Once you train an autoencoder in this way, you can actually use it to recommend items by just inputting at the input the full set of items that the user has watched, and seeing what is reconstructed at the output, right? What other items the autoencoder predicts are likely that you watch, right? And there are many versions of this kind of autoencoders for recommender systems, with some slight variation to add personalization, et cetera, et cetera. Another way these deep collaborative filtering methods are used is by taking user features and item features, right, and embedding them into a lower dimensional space, and then computing similarities between these two embeddings based on if this item and user have ever interacted with each other, right? If you have some information about the movie, the actors that are playing in it, et cetera, and some information about the user, demographic information, et cetera, you can embed that in the lower dimensional space and compute similarities between these two vectors, always using this deep neural networks, right? This is called the MVDNN method by Microsoft. Okay, another, as sort of the third area where deep learning methods are used a lot is extracting features from content. And this is actually quite a powerful, deep learning methods are quite powerful in this area. We go straight to the example. Imagine again the case of Amazon, right? A user not only reads the description of an item when he purchases an item, obviously, he also looks at the image. So it's reasonable to assume that the image contains relevant information about the user, right? So we want to include that information into the recommendation problem, right? So how can we do that? Well, we can do that. I mean, deep learning methods are very, very good in extracting information from images. We know that, right? So we can use a pre-trained deep neural network, for example, GoogleNet or VGG, or there's a whole class of pre-trained neural networks that you can download for performing image recognition, and use that deep learning network to extract features out of this image, right? And we can then take these features and include them, in this case, into a matrix factorization problem, but actually you can include them in any, almost in any deep learning recommendation system algorithm, right? And that's the main idea. In a similar fashion, you can actually train deep learning networks, convolutional neural networks, on raw audio, right? And this has been done back in 2013. And in this example, basically the neural network was trained in a way that it could predict the latent factors of a matrix factorization, which was done on the user-item interactions, right? But again, you can use this convolutional network straight on the raw audio to extract features out of the audio and use these features in the recommendation problem, right? And in a similar fashion, people are using currently also recurrent neural networks on text to extract information out of the text, for example, for paper recommendation or news recommendation, right? And map this text into a lower dimensional space and use this information to do recommendations. So obviously, and again, this is just a small example, small set of examples of how deep learning methods are used. There are many, many more papers in the literature on this topic, right? And finally, an area where we also have done some research, which we call session-based recommendation with recurrent neural networks. And you're all familiar with a session when you're buying something on Amazon, right? And here, what we mean with a session is, the sequence of click that leads you to a purchase, or maybe no purchase, right? So let's say you want to buy a coffee machine, and you start by looking at these coffee machines, right? So you do 1 click, 2 clicks, 3 clicks, up until you buy this, finally, this coffee machine, right? So this is what we call a user session, okay? And what do we have here? Well, often what we are lacking here is we are lacking past user information, right? Okay, Amazon, you might have an account on Amazon, but in many, many of the other e-commerce shops, you might not. So the e-commerce shop doesn't know which user it's dealing with, right? That's one thing. And the second thing is that there's obviously some order in this data, right? There's obviously some sequence that you want to model here to do proper recommendation, okay? And this data usually looks like that, right? So we have several anonymous users that do several sessions that are of different length as well. No, they might be very short or very long, right? So enter recurrent neural networks, which are actually deep learning methods for modeling sequences of data, right? They're used a lot in text, in natural language processing, audio, etc. And the idea in recurrent neural networks is, let's say, the main difference between deep learning methods, traditional, let's say, or simple deep learning networks and recurrent neural networks, is that the units in recurrent neural networks have some kind of inner state, right? Here we call it S. And this inner state is a function of the input and the previous inner state of the network, okay? So this means that as data comes into the network, into the recurrent neural network, this hidden state summarizes essentially more or less all the data, or at least the recent data that it has seen, right? So you can think of this hidden state of the network as a summary of the current data and the past data that it has seen, okay? And the output of this network is just a function of this hidden state. Okay, that makes these networks very, very good in modeling sequential data because they can recognize patterns in sequences. Okay, and so as I mentioned, if you think about traditional sort of recommendation systems or algorithms, they are really, really bad in this kind of task, in modeling sequential data, right, in modeling sessions. That's why we decided to use recurrent neural networks. And we actually used a special version of a recurrent neural network called the gated recurrent unit, the GRU. And essentially what we do is we take a one-hot encoded representation of the item, right? We use it as an input to this recurrent neural network. And at the output, we try to predict the next item that the user will click, right? Excuse me. So there are several tricks that we are using, but they are not that important. The main sort of change that we did to the standard recurrent neural network is that we use ranking loss functions, right? Because you can think of the recommendation problem as a ranking problem rather than a classification problem, right? And basically, the main takeaway here is that these kind of methods are about 30% better than sort of traditional recommendation systems in this task. And yeah, so we also took this a step further, and we actually did also a personalized version of this. And the idea here is that you might have anonymous users, right, that come into your system, and so you don't have past information about them. But you might also have users that you know their past sessions. So obviously, the information from the past sessions will be related to the information to the current session, right? So you might have users that like to watch sports videos, for example, right? And so here the idea is you could just concatenate the sessions and model them as a really long session, right? Or do something that we did using a hierarchical recurrent neural network. And the idea is here that you take the first session of the recurrent neural network and use the last hidden state of this session as an input to a second recurrent neural network, which will predict a good initialization for the hidden state of the second session of the user, right? So you have these two layers of recurrent neural networks. One that does the predictions for the next item, and the other one that maintains the hidden state of this between sessions, let's say like that, or transforms them between sessions, right? That's the main idea here. Just to wrap it up, I would say, 3 years ago, if you looked at the literature in deep learning, or 4 years ago maybe, and recommender systems, there was almost nothing. Nowadays, there was almost nothing that is not deep learning, right? The transformation has been complete, right? And I think we, and my group in particular, were quite of pioneers in that area. And of course, I mean, it's always good to to work with these methods with a little bit of skepticism, right? There's a lot of hype around these deep learning methods as well, but in general, they work really, really well in the domain of recommender systems. Okay, thank you.
Thank you, Alexandros, and thank you especially because you didn't have 15 minutes to set up, but you were super understanding even though you had only 1 minute to set up. Thank you very much for the flexibility. We do have time for just one question.
Sure.
Let's see which one got the most votes. Here we go. Traditional recommendation systems can start with a very small amount of data. How do you provide recommendations for the first customer with a DL-RecSys?
Okay, that's an interesting question. If you don't have any data, I mean, this is the typical cold start problem, right? And there what you can do is you can try either to bootstrap some data, use some kind of crowdsourcing, or use item characteristics, item features that you think are relevant that in your recommendation. But obviously, this is a very, very tricky problem, right?
Yeah, completely. I can totally understand. So will you share your slides link on Twitter?
Yes. I mean, if you just Google the deep learning for recommender systems, right? An extended version of my slides is on SlideShare, right? If you just say deep learning for recommender systems, it should be one of the first links.
Perfect. So that was Alexandros Karatzoglou. He will be here near the stage. So if you have any further questions, please come up to him and ask further questions.
Sure.
And we will see each other again at 11:45. Thank you very much.